How do digital filters extract specific sounds? Imagine listening to your favorite song and wanting to hear just the vocals or the guitar. Digital filters make that possible by picking out certain sounds from complex audio signals. When sound travels through the air, it turns into an analog wave. To work with it digitally, the wave is sampled at a fixed rate, like 44,100 times per second for CD quality. Each sample captures the wave's height at that moment. These samples are numbers stored in a sequence, forming a digital representation of the sound. Digital filters then step in to process these numbers. They use mathematical operations to change the signal's frequency content. Think of the sound as a mix of many different pitches, from bass notes to high treble. The filter's job is to let some of these pitches pass through while blocking others. For example, a bandpass filter allows only a specific range of frequencies, like those of a human voice, to come through. It does this by designing filter coefficients that shape the filter's response, making it high in the target range and low outside it. These filters work in the discrete time domain, meaning they operate on the sampled data, not the continuous wave. This gives engineers precise control over how sharply the filter cuts off unwanted frequencies. They can also adjust the filter's parameters dynamically, making it flexible for different situations. For instance, in noise reduction, the filter can be tuned to suppress background sounds while keeping speech clear. The filtering process involves several steps. First, the analog sound is sampled and quantized into digital values. Next, the filter processes these values using algorithms. Finite impulse response filters convolve the input with a set of fixed coefficients, while infinite impulse response filters use recursive formulas that feed back previous outputs. The design of the filter determines which frequencies are passed or blocked based on the filter's frequency response. This response is carefully engineered during the design phase using techniques like windowing or optimization. After filtering, the processed digital signal can be turned back into analog form with a digital-to-analog converter. This produces the sound you hear, now cleaned up or isolated. Digital filters are widely used in many areas, from improving call clarity by reducing noise to isolating musical instruments in recordings. They offer advantages like better noise immunity and easier implementation compared to analog filters. They also allow complex filtering that would be hard to do with analog components. In essence, digital filters extract specific sounds by converting analog audio into digital data, shaping the frequency content through mathematical algorithms, and then converting it back into sound. This process makes it possible to isolate, enhance, or suppress particular sounds with great precision and flexibility, all within the realm of digital signal analysis and processing.